start to the lecture by Ryo. Originally, we planned that this lecture would be given by Dakshita, but she couldn't make it because of some visa issues. So instead, Ryo will present this lecture, but I think the slides are from Dakshita, right?
Yeah, from Dakshita. Good morning. So, yeah, as Stefan told, this presentation material was created by Dakshita, but I will do my best to explain these contents. So I'm going to talk about how to delete information by using power of quantum information. So we can actually achieve many cryptographic primitives with certified deletion. In this talk, I focus on encryption with certified deletion. This is the syntax of this primitive. We have, she omitted key generation algorithm anyway. So we have a key generation algorithm, and we have encryption algorithm by using encryption key, public encryption key PK. And here is, for simplicity, plaintext is 1 bit, B. And so this is not in general, but in this talk, the construction, ciphertext consists of quantum part, CT1 cat, and the classical part, CT2. And this encryption algorithm also generates a verification key to verify that certificate for deletion is valid or not. And the encryption algorithm takes this ciphertext and recover the plaintext B. We also have deletion algorithm that takes this ciphertext and output the certificate B. I believe this is B, all right? And the verification algorithm takes this certificate and the verification key, the output valid or not. Okay? This is the syntax of encryption with certified deletion. So here is the informal security of these primitives. So as long as the adversary is, not PPT, I think, QPT, quantum polynomial time, bounded at the time it generates deletion certificate D, then we check this certificate B by using verification key VK, and after that, if this certificate is valid, then even if the adversary is computationally unbounded, B is hidden in information theoretic sense. This is the informal security of certified deletion. Is it clear? So we know that we cannot achieve public key encryption with information theoretic security. Here is some between computational security and information theoretic security. Before we check the certificate is valid, it is computationally secure. However, after we check that the certificate is valid, then we can guarantee information theoretic security. Yeah, sweet.
So it's obviously nice to remove B information theoretically, if we can achieve it, which I guess you can. But it's enough to remove it computationally, right? So that does not give us any savings?
Oh, sorry, what do you mean?
Like what I mean is, so what you said here is that verification of V implies that B is information theoretically removed. It would be sufficient to say that B is computationally removed, right, from A's view. So I'm saying it's very nice if we can achieve the stronger property of information theoretic security, but computational would suffice. But
right. So maybe in the future, the LRB problem is broken, right?
No. I agree with you that this is the best definition. I'm just saying that a weaker definition may have been okay, but probably the weaker definition does not help you in any way. Like, does it make sense? I mean, never mind. I think I'm just saying something very minor, but maybe I'm confusing it too much. We can talk later.
We can. Okay, so here is a more formal security definition. We consider this security experiment. So the left-hand side sheet is the challenger, A is the adversary. The challenger generates the key pair, public key PK, and secret decryption key SK. And in this experiment, B is fixed. So we generate ciphertext of bit B by using public key PK. And we send the public key and ciphertext to the adversary. And the adversary at some point generates a candidate of certificate B. If the challenger verifies that certificate B is valid under this verification key, then this experiment outputs the residual quantum state of the adversary role as an output of this experiment. And if this certificate is invalid, then we just output bot. And if the trace distance of this residual state rho, but in the, if certificate is invalid, then this output of course bot. And we consider trace distance between this experiment 0 and experiment 1, which means encryption is the ciphertext of 0 or ciphertext of 1. And the trace distance is negligible, then we say this is everlasting secure. Rho is the residual state of the adversary. So what the view of the adversary, whatever the adversary get.
Yeah, I just don't get it. What is rho? Is it some random state? Is it some quantum state?
Yeah, quantum state.
Random or who generates that state?
The adversary.
The adversary just generates his own state.
I mean, this quantum state is kind of what the adversary gets from this experiment.
Okay, and how this rho deals with this public key and ciphertext?
Sorry, say it again?
How does rho relates to ciphertext?
The adversary, given this information from the challenger, A can include this information in rho.
Okay. Okay, thank you.
Yeah, it's kind of all information after the experiment the adversary get. Yeah. Okay. Here this is the security definition of encryption with certified deletion. So before we go into the detail, explain applications of no, this is, so in this talk, I explain how to achieve certified deletion for many cryptographic primitives like public key encryption, commitment, and revocable time lock encryption, attribute-based encryption, witness encryption, free homomorphic encryption. In this talk, we see some kind of general compiler that takes standard cryptographic primitives, one of them, and into the same primitives with certified deletion. Okay? So if we use free homomorphic encryption as an underlying primitive, we can convert this into FHE with certified deletion, for example. And this technique also can be used to achieve everlasting security transfer, which means, we can also use, okay. So we, for example, there is a secure two-party computation. It is impossible to, in secure two-party computation, for example, let's consider oblivious transfer. There is sender security and receiver security. So there are two security notions for secure two-party computation. We cannot guarantee information theoretic security for both security notions. It is impossible. But by using the technique introduced in this talk, we can achieve something between computational security and information theoretic security. In secure two-party computation, here is Alice and Bob. So we can guarantee Alice is, I call this Alice is a sender, and Bob is a receiver. We can guarantee that information theoretic security for Alice, but sorry, security against unbounded Alice means for Bob, security is information theoretic security. For Alice, the security is computational one, because Bob is bounded, computationally bounded. We can achieve this kind of security for secure two-party computation. But using the technique in this talk, we can transfer security, information theoretic security from Alice to, from Bob to Alice. Okay. So after the end of the protocol, Bob does something. Bob does something, some procedure. Then we can switch the information theoretic security from Bob to Alice. This is everlasting security transfer. But I will not explain the detail of this protocol, but anyway, we can achieve this kind of new security notion. Okay, so there are many works on encryption with certified deletion. I briefly review the previous works of this content. This content is based on the work by Warsaw and Khurana, 2023. And Undu already introduced the notion of time lock puzzles. It's kind of a time released. As far as I remember, I think this is what is called time released encryption or not. I don't remember correctly, but yeah, anyway. This is very close notion to certified deletion. Broadbent and Islam explicitly introduced the notion of encryption with certified deletion in 2020. They achieved one-time secret key encryption with certified deletion in this in their work. But this is very very basic primitive because it is one time. Even it's not reusable and secret key encryption. And later, in my work, we improved the broadband and the Islam result. We achieved public key encryption with certified deletion and attribute-based encryption with certified deletion by using a technique of non-competing encryption. However, this security, what is achieved in this work is a little bit weaker than the security notion I explained at the beginning of this talk. It is achieved, it is everlasting security, but in this work, we consider the adversary is QPT, even if the certificate is verified. But after certificate is verified, the adversary receives the secret key to recover plain text. So it is a little bit weaker, much weaker than everlasting security because we still consider quantum polynomial time algorithm. And in another my work, we consider certified everlasting security for zero knowledge. And Porember also consider public key encryption with certified deletion. They use the learning with errors problem to achieve the primitive. And also he achieved the FHE with certified deletion in this work, but he needs some unproven conjecture to prove the security of his construction. And in another my work, we consider certified everlasting security as Dakshita Khurana, and we also consider functional encryption with certified deletion. So there are, this is some concurrent and independent work of Dakshita and Khurana. Okay. Yep.
So the question is about these quantum certificates. Is it meant to generate just a single certificate and to transfer it to some person who will possess it? Or do you try to generate several copies of this quantum certificate?
Okay, so certificate, in this construction, certificate is the ciphertext itself, quantum ciphertext itself. Just we return given quantum ciphertext as a certificate. Yeah. So yeah, I think, yeah, of course, classical certificate is better. So, but in this work, the certificate is quantum.
Okay. Another question. Can we talk about everlasting encryption if, as far as we know, all quantum states will decay?
All quantum states
will decay. So all quantum states will lose quantumness after a bounded time.
So your question is in that setting.
Can we here have some scheme to transfer the quantum the certificate from quantum state to quantum state before it decays, or because the statistics the statistical physics, the thermodynamics, prevents us from having eternal quantum state that is eternally entangled?
I didn't correctly understand what he said.
So I understand that in this encryption, the certificate is quantum state, right?
Yeah.
And the quantum state will end, lose quantumness, become classical after a while. So can we prevent that somehow?
So your question is why we can achieve everlasting security after?
Yeah.
I'm not sure whether why it is prevented that from achieving information security. Maybe we can talk offline. Okay. So let's see how to achieve encryption with certified deletion. We will look at the construction by Warsaw and Khurana, and this is a background. And so we use BB84 state, or it is called Wisner state, Omri explained yesterday. So I think the presentation is a little bit different from that by Omri, but yeah, I explain again. So we use computational basis and Adamar basis, and here the notation, I explain the notation, ket x sub theta means, so x is a bit string, can be considered bit string, 0, 0, 1, 0, 1, 0, 0. So for, like, we consider n qubits, something like that. So theta is called basis choice. If theta is equal to 0, we choose computational basis, which means that we encode the bit x into qubit 0 or 1. And if we choose basis theta is equal to 1, then we apply Adamar gate and get the superposition of 0 and 1, ket 0 and ket 1. And this is essentially the same what Omri explained yesterday. Is it okay? So we use this notation in this talk. And if we use computational basis for measurement, if theta is equal to 0, then we can measure ket 0 or ket 1 with probability 1. If the x is equal to 0, then we should measure 0. But if theta is equal to 1, this is encoded in this superposition state. So if we use computational basis measurement, then we measure 0 with probability half and measure 1 with probability half in these two cases, plus ket and minus ket. If we use Hadamard basis measurement, these are flipped. Okay, if we use Hadamard basis measurement, we measure plus ket, then we get a plus ket. If we measure ket 0 or ket 1, then with probability half, we get 0. We get 1 with probability half. Okay, we use this state. I call this BB84 state in this talk. Okay, so before go into the encryption with certified deletion, here is a notion of revocable secret sharing or secret sharing with certified deletion as the first step. So we consider Alice as a dealer, and Bob and Charlie received a secret share from this dealer, Alice. Alice want to share secret B by using this revocable secret sharing scheme. And Alice generate quantum share, get share 1, from secret B, and she also generate a classical share information, share 2. And Bob received this quantum share, and Charlie receives classical share. We have a reconstruction algorithm that takes these two share, quantum share and classical share. We can recover the secret bit B from these two information. And we can revoke this share, quantum share, by using deletion algorithm. If Bob run the deletion algorithm to this quantum share and generate classical certificate row, classical certificate B, and return this certificate to the Alice, to Alice. If this certificate is valid, even if Bob and Charlie collude, even if they collude, they cannot get information about B. This is a revocable secret sharing. So if before Bob delete a quantum share, if Bob and Charlie collude, of course they can recover information B. But after Bob generate a certificate B, which is valid, then even if they collude, they cannot get information about B. Okay, here is how to achieve this revocable secret sharing. Alice choose X and theta, their n-bit information. X is used for encoding, and theta is base choice, as I explained. And Alice send BB84 state, ket X sub theta, to Bob. And Alice also send theta and B XOR parity of X. Parity of X means X or of or I bit of X where theta I equals 0. So this means parity of X is XOR information for all computational base choice part. Is it okay? Okay. Yeah, and Bob and Charlie, if we correct these two information, of course we can recover information B, because we know if we know theta, we can completely recover information X from this BB84 state. So we can compute this parity of X and get the B. So we can achieve the functionality of secret sharing by this scheme. Now let's look at how to revoke this quantum share. Bob, to generate a certificate of deletion, Bob measure this BB84 state by Adamar base and send the resulting information as B to the DRAM Alice. So B is a measurement result by Adamar base. Alice checks this certificate by using X and theta. So the Alice check for I such that basis choice is Adamar basis, whether this certificate BI is equal to XI. Okay, so if Bob honestly measure this BB84 state by Adamar basis, then the Adamar get cancelled, and we can get the original information X. So it is easy to see that if Bob honestly measure this BB84 state in Adamar basis, this equation holds for all I such that theta I is equal 1, Adamar basis choice. Okay?
So why, I'm missing some basic thing, like why is it important to measure in the Hadamard basis? So here the choice of basis is a random choice by Alice, right?
So you mean that why doesn't Bob measure in computational basis?
Yeah, I mean, a natural thing to do, in my opinion, would be to flip a coin and measure in one of them. But why are we fixing the basis here?
Right. Good question. It is not important we choose Adamar basis for here. If we, at some point we use some computational basis measurement, but if we, of course Bob can use computational basis measurement. Yeah. Then after that, we use at some point Adamar basis measurement in another point. Anyway, so yeah. It is not irrelevant whether we use Adamar basis measurement or computational basis measurement here. Yeah.
So, I mean, with probability half, you will, so with probability half, you recover X when you do the measurement, right?
Yep.
So, even though you sent the measurement back, how did you revoke the secret? Because with probability half, I know X and therefore parity of X, and I can still reconstruct the secret with Charlie.
Okay, so let's see the case of we use Adamar basis choice. Okay. So Bob doesn't know basis choice theta at this point.
Yeah.
So yeah, if Bob knows the basis choice, then it is easy for Bob to cheat Alice. However, at this point, Bob doesn't know theta, so
maybe the fact that you cannot do it with probability half is the important thing, and you'll repeat it several times.
Yeah, right. So yeah, we use n bit information here. So right, X and theta is n bit, right?
Yeah.
So it is unlikely that Bob can cheat for other bits.
It's because you're repeating it so many times. Okay, got it. Yeah.
Other question? Okay. So yeah, this is okay. So sorry, so this is a construction of secret sharing with certified deletion, and yeah, we can use this idea for encryption with certified deletion. Okay, so now Alice is not the dealer. Alice is the sender of encryption. Alice wants to encrypt bit B. So Alice choose X and theta and generate the BB84 state. And she also generates a ciphertext of theta and B prime. B prime is Bx and the parity of X. So she masks bit B by using the parity of X. This is exactly the same as, oh, no. So the BB84 state is exactly the same as Bob's share in the secret sharing setting. Now, instead of send theta and B prime directly to Charlie, we encrypt this information because we want to achieve encryption with certified deletion. This is the encryption algorithm of this construction. It is easy to see that we can recover the plain text B by using decryption key of this encryption algorithm. Oh, sorry, I didn't explain formally. We convert standard public key encryption into public key encryption with certified deletion. So we use a standard encryption algorithm here. So we generate a key pair of standard public key encryption. And so Alice received the public key, and the receiver, maybe Bob, I call it here. Bob has a secret decryption key, SK. So from this classical ciphertext part, it is a standard ciphertext of standard encryption scheme. Bob recovers theta and B prime. Okay? And Bob also has BB84 state. So Bob can decode X by using theta. And now Bob can unmask this bit B prime by using parity of X. So Bob can get information B. This is the decryption algorithm. So far so good? And the deletion algorithm is basically the same as the deletion algorithm of the secret sharing. Here, maybe, okay. We measure BB84 state by Adama basis, and the resulting information is a certificate of deletion. So here, I didn't explain the verification key. Verification key consists of X and theta. If we have these two information, we can check the certificate is valid or not. We check that the certificate is equal to X for all I, such that the basis choice theta I is equal to 0, meaning equal to 1, sorry, Adama base measurement. Okay. Yeah, here is verification algorithm. Yeah, bottom. Good. Yep.
Okay, so the first question is just to clarify that the deletion operation just spoils half of the bits of the secret. Okay.
Yep.
And now about the whole construction. So either Bob decrypts everything and gets the secret bit B, or somebody spoils this whole protocol and nobody gets this B, right? Am I right?
So Bob, okay, recover B. Yeah, in the I mean honest setting, if Bob has a secret key, it is okay that Bob recover plain text B. Yeah.
Okay, so we cannot delete the message from Bob. So if Bob gets it, then he gets it forever.
Yes. Of course, from Bob cannot prevent. We cannot prevent Bob from getting. Yeah. So let's consider more concrete setting where we need this kind of primitive. So maybe we can store the ciphertext to some cloud server. In this setting, maybe we need some quantum computer for the server. And so at some point, we download the ciphertext. And maybe we require the server to delete information. I mean, delete the ciphertext. Because, maybe secret key is compromised at some point. And then the server also breached it. Then information about plain text it may be leaked. But if the server generates a certificate of deletion, then it is guaranteed that even if the server is breached, there is no information about the plain text. Yeah. But if we cannot prevent the original sender Bob from recovering the plain text. Okay. And okay, so this is exactly the same I explained already. So yeah, this is a summary of the scheme. So the encryption algorithm generate quantum ciphertext and classical certificate. Quantum ciphertext consists of BB8 post-state. Classical ciphertext is encryption of theta and mask B. Okay, decryption is easy to see. Just we recover theta and B prime from the classical certificate and measure the quantum ciphertext in basis theta to obtain X. And then we can unmask B prime. And the deletion algorithm just measure the quantum part of this ciphertext in Hadamard basis. Yeah, and verification key VK consists of X and theta. So yeah, I want to mention that this information, VK, should be hidden from the adversary. Otherwise, if X and theta are revealed, the security is lost. So VK should be secret in this setting, in this construction. Okay. This is the scheme. Questions so far? Okay. So yeah, this is again the security experiment of encryption with certified deletion. The challenger generate key pair PK and SK and generate ciphertext of B and send the public key and ciphertext to the adversary. The adversary at some point generate a certificate B, and if certificate B is valid, we have to put all information that the adversary get. And we consider the trace distance of the to experiment where B equals 0, 1. And if this is negligible, it achieves the certified deletion security. So how to prove this security notion? Let's consider the sequence of game experiment of security. Here is somewhat concrete barriers of the construction and put them into this security experiment. yeah, we send the public key PK, and the ciphertext consists of the BB84 state and the encryption of C and B prime. And the certificate is X prime. We check the certificate is valid or not by checking all i's bit such that the base choice is equal 1 Adamar basis. And yeah, if it is equal for I, then output the residual quantum state of the adversary. So the point is that we need to consider security against the computationally unbounded adversary after the certificate is verified. How to prove this? Sigma. Oh, sigma is some, I think this is auxiliary information is given to the adversary. James, right? I guess. Yeah, initial auxiliary input to the adversary. Yes, okay. So now let's consider the next experiment. So we choose bit shooter at the beginning of this experiment. And instead of using B, which is the original plaintext, I think, we use B children for masked ciphertext. And yeah, we send the public key and the ciphertext and receive the certificate. And if after the challenger receives the certificate, if B tilde is equal to B, then do the same thing as the original experiment. If it's not equal, then output both. So with probability half, this experiment is exactly the same as the original experiment, right? B tilde is just a random coin. It's irrelevant to the original plaintext bit B. Just a random coin, B tilde. So with probability half, this is equal to B, and it's completely the same as the original experiment. Good. So next game, experiment 2, is like this. Instead of we generate BB84 state for quantum ciphertext, we generate EPR pair for here it's K. Yeah. This should be N, I think, because this slide use N, I think, for, oh no, here is K. Okay, anyway, it's okay. It's the same length and the basis choice. Okay, we generate the EPR pair instead of BB84 state. And so the left register is called register A, I, and the right register is called BI. And we send register B as quantum ciphertext to the adversary instead of BB84 state. And after the challenger receives the certificate X prime, the challenger measure register AI in basis theta I to get Xi. And then compute B childer okay, B tilde is B prime X or parity of X. And well, yeah, if, we will also abort if B tilde is not equal to B. Actually, this is, so yeah, we don't generate the BB84 state explicitly, but it's completely the same as we generate the BB84 state from the view of adversary. This is a very standard trick used in quantum cryptography. Yeah. So this experiment is completely same as the previous experiment.
So what's the question, like why did we replace the previous thing by the NCBR pair?
So you're asking why it is equivalent. Is that your question, or why we use EPR state?
Yeah, the second.
So we can defer the measurement. So we don't need to choose X at this point. We can defer using X after we receive the certificate from the adversary. This is a trick. A very good question. Okay. So what we want to do is to prove that trace distance of these two experiments is negligible. Okay, so now we consider the third experiment, which is basically the same as the previous experiment. However, we encrypt zero padding and B prime instead of theta and B prime. This is the third experiment. So we want to say that I think we want to say that in this experiment, the trace distance of experiment 3.0 and experiment 3.1 is negligible. What we want to say is, I didn't explain why experiment 2 and experiment 3 doesn't have a significant difference. But before that, I explained why in this third experiment the advantage is negligible. The trace distance of these two experiments. Okay, so to look at this, this is a result by Bowman and Pell. So here is left is a challenger and right is adversary. So we sample the EPR pairs, right, at the beginning of the experiment, and send the right register to the adversary and keep the left register. And we expect that the adversary measure this register by Adamar basis and send the resulting information to the challenger. Here, sample subset S from set N, and the size of S is N over 2. Okay, N half. And for all I in this set, measure register AI in Adamar basis to obtain xi and check xi is equal to xi prime. This is essentially the same as the verification algorithm of the certificate. Okay? So then, with high probability for all I not in S, so the complement of S, AI is close to xi prime encoded in Adamar basis. I believe that this notation ket sub H is this information is encoded in Adamar basis, right, James? I think, yeah. And so this is a projection onto this state. I believe that this delta means delta means Hamming weight of y x or x prime. So which means number of different point of these two strings. Yeah, here is Hamming weight, of the x over y and x prime. And then this is less than c. I think c is just a constant, like half. And this Bowman-Ferrell claim says that in this setting, with probability 1 minus negligible, this state is projected onto this state. So what this means? So if we checked Adamar basis part of the returned certificate, except negligible probability, other part is uniformly random. Okay. So we want to use again. So as Shweta asked, that intuition is very simple. If Adamar basis part is correct, I mean the verification, the certificate passes verification, then the adversary has no information about computational basis part. That is the intuition. Okay. And let's get back to the third experiment. In this experiment, theta is not in the ciphertext. So we sample theta after the challenger receives the certificate and measure the left register AI in basis theta I to obtain x. And we can do the same thing as the experiment. This is okay. The third experiment. Is this next slide? Okay. And we can check this condition by looking at measuring the first register of the EPR pair by using this projection. And we can check that the certificate is correct or not by looking at by measuring the left register. Okay. So what we want to say is that okay. Here, this lemma said that this lemma is by Glover, Basek, Khurana, and Kumar. This roughly said that if the Adamar basis choice part is correct, then the computational basis part is independent and uniform bit. So if a certificate passes the verification, The masked part is XOR of all xi, where base choice is theta. Theta is equal to 0, a computational basis part. So that XOR part is completely uniform, random B. So we can mask the information B by using the computational basis part. So in the third experiment, we don't have any information theta from the view of the adversary. We can say that the trace distance of the third experiment, the case of B equals 0 and B equals 1, is negligible. But what we want to say that the trace distance of the second experiment, experiment 2 sub 0 and experiment 2 sub 1 is negligible, which is different from the third experiment. But if there is a non-negligible difference between these two second and third gain, it contradicts to the CPA security of the standard public key encryption scheme. So we can say that trace distance of second experiment, experiment 2 sub 0 and experiment 2 sub 1 is negligible. So this is what we want to get. Okay. And this is actually very general tool. Not if we use commitment instead of a standard public key encryption, we can achieve certified everything security for commitment. Just we commit C and B prime instead of directly commit B. We can use other encryption algorithm like attribute-based encryption, free homomorphic encryption, or witness encryption. Yep. Okay, so we have 25 minutes. Now, so there are several follow-up works. This shows application to CCA secure encryption, maliciously secure blind delegation, and obfuscation, and functional encryption. Yeah, we can consider certified deletion for these other primitives, which is studied in other works. I want to talk about the public verification version of this notion. So I said that VK should be hidden from the adversary in that scheme, because if X and theta are revealed, the security is completely broken, right? So the question is, we can publicly verify the certificate is valid or not. It is a very interesting question. So yeah, we can do this. 3 follow-up works achieve the public verification. And I want to switch to another slide, because this is part of my work. Okay, so how to verify, publicly verify the deletion certificate. This is a joint work based on Kitaga and Fuyuki Kitaga and Takashi Yamakawa. Okay, so this is not tuned for this talk, so I skip some background. This is a brief review of the encryption with certified deletion. Okay, certified deletion security. Yeah, prior work. So. What I explained is privately verifiable. We need to keep private verification key BK. So in previous works, actually public verification was achieved by using strong assumptions like extractable witness encryption. Okay. And later, Bartek, Khurana, and Bremba improved the assumption. We can achieve public verification by using almost regular one-way function, which is very basic, weak assumption, but it's not perfect. We want to use just one-way function, standard one-way function. We do not assume almost regularity. So the question is, we can achieve public verifiability from weak assumption. Okay, so yeah, this is a brief review of Bartek Khurana compiler. This works secret key encryption, public key encryption, other description, many encryption type primitives. But the disadvantage is secretly verifiable because the verification key consists of X and C. This is just okay. So again, as Shweta asked, it doesn't matter whether we use Adamar basis measurement or computational based measurement to generate a deletion certificate. If we use the computational based measurement for deletion, then we just check the computational based part of the certificate. And this is yeah, almost the same as the security, what we look at for the security proof of the construction. The ciphertext consists of BB84 state and encryption of theta and the masked plain text. And yeah, we check the certificate for computational-based part and the trace distance of the two experiments. So we want to convert it into publicly verifiable one. How to do this? We use a signature, very basic primitive. But we cannot sign quantum state directly, but we can generate a signature for the register. We apply the signing algorithm to the register and write the resultant signature in the second register. So sigma 0 means the signature for 0, and sigma 1 means the signature for 1. So if we apply this signing unitary, if we apply this to this superposition state, we get the superposition state of this state, ket 0 and ket signature for 0, and or the superposition ket 1 and ket signature 1. We write the signature in another register. We can do this. So our compiler is like this. It is publicly verifiable. Instead of directly send BB84 state, we first apply this signing unitary, which generate a signature for the bit, and we encrypt signing key of this signature algorithm, and the theta masked plain text. The verification key is now the verification key of the signature scheme. Deletion is just measure the quantum part in computational basis. And the measurement result consists of X prime and sigma prime. And verification is check all signature for all j. So signature is signature for bit 0 or bit 1. And this is written in the second register. If we measure in computational basis, then we get signature for 0 or 1. We check all signature by using the verification algorithm of the signature scheme. We do not check by using the basis choice and bit string X. Just we check signatures. So it is publicly verifiable, but because we only need this verification key of the signatures. Yeah. So here is our lemma. Now the adversary is given public verification key BK and not BB84 state applied this unitary of the signing algorithm and encryption of secret signing key theta and mask prints. Even in the verification is check all the signature. Yeah, even in this setting, trace distance of two experiment is negligible. So how to say this? It's very easy if we assume the Bartek-Khurana lemma is true. We can delete the information about the secret signing key by using the security of encryption, like we saw that theta is hidden from the adversary. So, and if for some j such that the basis choice is equal to 0, it means computational basis, x prime sub j is not equal to xj, and the signature is valid, then it breaks the unforgeability of the signature scheme, right? Because the adversary get the signature for different message if adversary achieve this. So, if Bartek-Khurana lemma is true and the signature scheme satisfies the unforgeability, we can say that our lemma is true. And we only need just one-time signature for this purpose, because this adversary sees only one pair, X sigma. And the rest of the is not so important. So yeah. Okay, so the point is that by using standard signature scheme, it is easy to transform the compiler to the publicly verifiable one. That is what I want to say. And so we get it's not human. Yeah. So for example, we can apply that compiler to standard public key encryption, which means that we assume the existence of public key encryption. It implies the existence of signature scheme. So we don't need any additional assumption to achieve public verifiability. Yeah, so we can achieve the public verifiability with such publicly verifiable deletion with from minimal assumptions. Because we want to apply the public key encryption or some other encryption scheme. So yeah, we can, yeah, it's okay. Okay, so yeah. That's it.